Hello, good morning, everyone. So my name is Pavan, and I'm a senior software cloud engineer in Grainger. So today I'm going to have a conversation with you guys, because I'm not from the HPC background, but I'm from the CNCF background. So we are going to have what are the tools we use it and how those can be leveraged for the CNCF is our target over here. So before going, so this is my bio. So where I contribute for a lot of CNCF projects like KEDA, ArgoCD, and Crossplane, and Dragonfly. So these are some of the projects I contribute. And I'm also an active Cube astronaut where it recognizes, the CNCF will recognize with all the Kubernetes certifications. So before going to that, so let's look at the traditional HPC, which heavily relies on the manual scripts or complex dependency management. This creates a reliance on a tribal knowledge results in the acknowledging the long change windows. On the other side, the CNCF we utilizes heavily on the GitOps, where it is heavily on declarative configs, like the Kubernetes orchestration or self-service platform or the instant rollbacks. All the AI and ML loads are what we call the blurring the lines between these two worlds, meaning we can adopt these the industry standard DevOps techniques, which can be also be try to apply on the HPC. That's our main motive for this. So yeah. We have massive pain points in HPC deployments. We have some manual scripts, maybe customized per cluster, or we have long deployment cycles taking for hours for stall innovation, and we suffer a configuration drift where somebody changes right away on the actual state, but those changes are not tracked or trailed, audit trailed or anywhere else. So that's where we have in CSCF at the GitOps tool, where what we can do is we can have Git as a source of truth, where we can have a initial instead of traditional push model, we can have a pull model. For example, you can take any tool for the GitOps tool like ArgoCD or FluxCD, where it resides on the cluster, inside the cluster, and continuously watches your GitHub repo, whether these changes, whether there's any change on your repo or something. And if there's a change, it automatically triggers the change and makes sure your whatever the changes you have it's with your desired cluster state or not. So that's what we are going to have it. So here we have multiple pillars. So the first pillar, I want to talk about the continuous delivery using ArgoCD. So when we define the workloads as an Helm charts or some stored configurations like a job templates or GPU quotas in Git, the ArgoCD continuously tries to check which is residing on your cluster, tries to continuously check your GitHub repository, and tries to see what are the changes you pushed it. So these changes can be no need to be any imperative, no need to write any manual comments or something. You can just write your imperative declarative YAML file. So once you see the ArgoCD continuously monitors that and then sees okay, there's a change happened in your GitHub repository, because that's where the exact source of truth is there. And it will automatically pulls the change and deploys into the cluster. And if there's any change that has happened beyond these changes, whatever it's in the Git, it will try to roll back immediately. So that's we call a self-healing. So whatever it's in the Git, that reflects on your cluster. So this impact is really massive for our deployments, because that's where generally the deployments used to take for about 2 to 4 hours. That drastically decreased for 10 minutes, and that too we used to have entire full audit trail and then the instant rollback capacity. And the second pillar that I want to discuss about is the Crossplane. Instead of waiting on a large IT tickets or for the developers to have a self-service GPU clusters and for the Git commit to happen, so it all happens everything with just a Git commit. And there's a lot of control that you can do it. For example, a team comes and says hey, I want to create a cluster with a specific GPU, and they don't have any guardrails. And your company says, okay, I have so-and-so budget. But the thing is you can't control if it is if you're not using any guardrail stuff. So that's where the Crossplane helps it. And you can create your Crossplane composition in such a way that, okay, these are the worker nodes or these are the instances that are allowed for that, and you define a template for them, and all the app teams has to do is like they have to just create an EKS claim. So as you seen in the screen, it's just like a claim where you mention what type of instance you want and in which region you want to create and all the stuff, and that's it, boom. Whenever you commit the change, it will automatically create the cluster for you, and there's a pre-warm instances that pulls up the stuff. So in the background, everything happens with the composition. That's where the platform engineers happens to do all this composition and everything. And as a end user, you just need to have this claim. So that makes life easier. So the third pillar I want to focus on this one is the KEDA. The KEDA stands for Kubernetes Event-driven Autoscaling. That's where like HPC workloads are incredibly bursty, and you can might be going for the zero queue depth. Suddenly, you have like a 500 jobs that arrive, and sometimes it goes down all of a sudden. So that's where like KEDA continuously monitors the queues like SQS or Kafka or what are the operators. So there are multiple operators that are available right now, and even the open cost, like based on the cost metrics also, you can do an auto-scaling. And rather than like regular HPA, the KEDA acts as like based on which trigger event you want to do it. So that's what we call a source. And based on the source, you try to do an scaling up and down. And which, like the most importantly is like when you have a queue empty, for example, in the night or something, and the KEDA detects, okay, there's no workload that is happening, and immediately scales down to 0, so that like no pods are running or no workloads are there, so there is no need or wasting of that money. And if there's like huge amount of money that like a huge amount of spike happen, like a lot of pods or workloads that are running up, and it needs a huge amount of workload, so it automatically scales up the stuff. Another one I want to stress on is like, okay, we have everything, the KEDA, all this Crossplane, ArgoCD. So that's where we need to worry about like the observability, because we need to see like, okay, what are the things that we need to observe, like how those are working fine, and if there's any metrics that you can do it per job, resource utilization or distributed traces or any pipeline bottlenecks, anything like we need to monitor. So that's where the OTel helps us. Like, so Open Telemetry is like one of the open source one that you can use it. By having the unified across our HPC environments or cloud native environments, we reduced our mean time resolution by like almost 40%. So what I learned from these, all the contributions is like, so we don't need to get right away jump into all the projects at once. We can start with one and start small for like non-critical environments like dev environments. And once we leverage, and we can jump into other tools like the ArgoCD, Crossplane, or KEDA based on the requirement we have it. And finally, it all depends on like how iterate safely we do it and the Git versions we do it. And so these are some important numbers we observed in our company. So like for the deployments, previously, before going to all these open source projects, we were like deployments used to take a longer time, but now the deployments are like faster by 95%, and which dropped from hours to 10 minutes, and even the infrastructure scaling, and that like it's almost like even for small EKS upgrades, it's used to take like almost like 3 to 4 hours. Right now, for an EKS upgrade, like from 1.34 to 35, it hardly takes like maybe in a couple of minutes for us. So, and each cluster used to have like almost 50 to 60 nodes for us. And we have like almost 10 to 15 clusters. So the cost, because KEDA used to scale up and down based on the workload capacity that's coming up and number of pods it's coming up. So KEDA decreased like almost like 30% of the cost for us. And coming to troubleshooting, yeah, it's OTel really helps, like Open Telemetry helps us like really like 40% of faster than what we expected. And we have complete audit trail because we have source everything declared in the GitHub. So anytime we want to have it, we can just look back and see what is happening. Yeah, and these are like some of the key takeaways I want to stress about. So one is the GitOps for HPC and the infrastructure as a code, where you can use the Crossplane and smart auto scaling with the KEDA and observability with OTel. And we have like a lot of, these are all the open source projects which we can have take a look of it. And as I mentioned, the ArgoCD. So this is where the ArgoCD application YAML looks like. So this is just a CRD that runs on the cluster. And if you take a closer look of it, it defines it's just a simple YAML file where you define the server is where exactly you're going to deploy. And it's no need to be that ArgoCD has to run on every cluster. It can do as a workload and management model where the management has all your deployment or infrastructure related stuff, and your workload is actual workloads that are running it. And there's no other platform-related stuff that are installed on workload, so there is no extra overhead that is running up. So your management continuously observes the workload cluster, and that does the job for you. Coming to, there's a final slide, I have it. So which is shifting left. We don't need to just fix the drift after it happens. We can prevent it before. That's what we can have a Helm template render in the GitHub pipeline itself, so that it exactly renders how the ArgoCD renders. So there is no need to worry about whether it happens later or not. And there's one more additional slide for this one. So this is where policy as a code. So this is where we just, it's up to us. We can have whatever the tools we have. We have Kyverno or OPA or there's multiple tools that are available. We choose Kyverno because that's most flexible with our Kubernetes environment. So you no need to learn any new language or Rego or something. For the OPA, you have to learn that. So this is where the cluster policy looks like. So what is exactly the cluster policy does is it just tries to enforce a policy which tries to block any images that are coming outside of what you're not expecting from. For example, if you're expecting to have an image only pulled from a specific ECR or Azure container registry, and you define over here, so there is no need to, so you are blocking any other images that are pulling from outside, so that makes our environment more security. So yeah, that's pretty much so. So this wraps up on the platform layer, and I have the continuous session for this one where I'm going to handle the various Kubernetes in depth, how we are going to have various stuff how we are going to handle and the package for the HPC containers or MPC scheduling, or even the extra level of hardware observability, how we can do it. Yeah, so these are, so yeah, that's pretty much I have it. Any questions? No, actually we are over the time. Thank you.